But while I was transferring it, I have quantized them to 8-bit precision. Now I use this command, assemble network, because this is a layer graph structure. There are structures in MATLAB Deep Learning toolbox. You have to learn them. You cannot train this structure or predict this structure. You cannot make a forward run on the layer graph. You have to convert it to a parent structure, which is called the network structure. So AlexNet's type is, as you can see, AlexNet's type is a layer graph. But if I choose AlexNet, so I'm going to jump there. So I'm going to step, and it's going to assemble network. So as you can see, this is a serious network structure, and it includes these layers. Actually, sorry. Okay, now I have my AlexNet. I have my AlexNet, and I have the AlexNet. My AlexNet is 8-bit quantized weight values, has 8-bit quantized weight values. The AlexNet is original. What am I going to do is, I'm going to load an image. So let's say, what is that image? Let's see. It's in my folder, and if you download the code, you'll find it as well. Oh, it's a cat. Actually, these kinds of cats are called tabby. Tabby, this. Tabby. If you check Google, you'll learn what is tabby. Anyway, so I load it. I make it single because it needs to be, the predict function needs singles. And I step up. So the AlexNet result is the activation of the last layer. The activation of the last layer are the probabilities, guys, of 1,000 categories. 1,000 categories. So I'm going to check the maximum of the 1,000 layers and find the index of it. This function, find, parentheses, AlexNet results equals to maximum AlexNet results, which means find the index of the AlexNet results which has the maximum value. Then I get that index and put it into classes, and I display it. As you can see, it is tabby. The AlexNet original network could find it. Can my quantized network can it also find it? Let's see. This is my AlexNet results. I feed my AlexNet to predict, because predict is the forward run of this net. It's going to give us the activations of the final layer. Okay, so my AlexNet results is a bunch of probabilities, and if I display them, it is also tabby, guys. So even if I quantized it, it worked for me. Well, this is nice because I see that at least for this image, the quantization didn't give any harm. I can try it for 4-bit quantization and get my results. But more importantly, if you want to test if your quantization had any side effects, you can do two things. For a single image, you can check if the probabilities have changed. So let's get the probabilities. AlexNet results. The AlexNet results. With the index, find the maximum. So this will give the probability of that layer, sorry. So the probability of the tabby was 48%. I mean, this might look a bit lower to you because when you look at that image, it's not 100% tabby cat for you. However, AlexNet is choosing between 1,000 categories, so it is by far the maximum. So did the probability change for my AlexNet? So I'm going to do the same check for my AlexNet. Find AlexNet results of the maximum of the AlexNet. Yes, the probability is a bit lower. So some things changed, but it didn't affect me for this particular image. How to test if it did affect me for many images? Well, you get many test images, thousands of them, hundreds of thousands of them, or millions of them, from different categories. And you check those images category-wise, if they changed anything and if there's any loss in accuracy for some category, and you make that analysis. That's how you do the analysis. Actually, this is a very nice subject for a project in our course. You could do this for an inception net, and you could designate a big network, and you could check the effect of quantizing weights to different levels of precision, and see the effects in different categories. And maybe you are going to find out that the tabby, the cat, the animal categories are not affected much, but however the some other types of categories like internal outdoor, indoor places, playgrounds, they will be affected. These will be scientific results for you. Okay, that's how you do the analysis. I'm going to repeat the same experiment once again with a lower precision, guys. I'm going to make the precision low. Okay, let's run it. How it's going to act. And it changed, guys. It says bear skin. Not a bad choice, but we've lost. So 8-bit precision was okay for this image, but 4-bit precision was not. Let's check the probabilities. Let's check the probabilities. My AlexNet. The probability is 61, and the AlexNet result probability is the same. So when you make it 4 bits, things change much. Let's make it 6 bits, although it doesn't make sense, but let's try a theoretical trial. Egyptian cat. Still it finds a cat, but it says another type of cat, guys. So as you see, quantization will affect us. How does it affect us, and to what extent we can do quantization is a matter of testing. And actually what we've done now is we've quantized the pre-trained weights. Actually this is not the right way to do it. The right way to do is to do quantization aware training. And quantization aware training is something quite complex. And in the next week's slides, in the next video, we are going to cover this concept, quantization aware training. Thank you, guys. This was the live code session of quantizing pre-trained weights. See you again soon. Bye.